All right, let's have a look. As we can see, we're looking at electrodynamics today. Let's go through the first few slides. This is more revision than anything else. We know that when charges move, a magnetic field is formed, and current, of course, is just the rate of flow of charges. So in other words, when current flows through a conducting wire, a magnetic field is going to be induced around that current conducting wire. Then magnetic field, our grade 10 definition there, just a region of space where a magnetic material will experience a force, and the symbol for magnetic field is a B, a capital B. It's a vector, of course. Then I just want to remind you of these two symbols. When a current or a magnetic field is going into the page or into the board, then we've got, or sorry, out of the page, then we've got a circle with a dot coming out of the board, and then into the page we've got a circle with an X inside. It's like an arrow going away from us. And then we can see just a solenoid is many loops of wire wound together to form a coil. So multiple coils next to each other, and then an electromagnet is something that produces a magnetic field only when electrical current flows through it. Then we can see Faraday's law. This is the most important definition there, that the induced EMF in a circuit is equal to the rate of change of the magnetic flux through the circuit. So we can see the EMF, or epsilon, there is equal to negative N, that's the number of coils, multiplied with the change in phi, that's my change in magnetic flux, divided by the change in time. And remember, whenever I take a change divided by change in time, then we say it's the rate of change. All right. Magnetic flux density or magnetic field strength, that's B, is measured in Tesla. We can use the symbol T. Magnetic flux, on the other hand, that's the product of the component of magnetic field perpendicular to a surface and the area of the surface that the field passes through. So we can see B, that's the magnetic field strength, A, that's the area enclosed by the coil, and then cos theta. Theta there, as you can see, is the angle between the normal, that's perpendicular to the surface, the normal of my area, and the magnetic field. So it's the angle between that normal and the red magnetic field. That's the theta there. That's the angle that I'm measuring. Then we can have a look at the induced EMF through a solenoid. All right. EMF is induced that creates a magnetic field that opposes the increase or decrease in flux, and the reason for that is Lenz's law. Nature abhors a change in flux. So basically, when a magnet is brought brought towards or away from a coil, the magnetic flux is changing. When it's brought towards, magnetic flux increases. When it's taken away, my magnetic flux decreases. That's because there's more penetration of those magnetic field lines through that area. Electromotive force, or EMF, or epsilon, that's the energy per unit electric charge that is imparted by an energy source such as an electric generator or a battery. So if we have a look at this diagram here, we can see we've got a coil that's a black rectangle that's a little bit oblique, and then I've got a magnet that's either brought towards or taken away from that coil. All right, we're going to be using our right-hand rule here, our right-hand solenoid rule. We can use this in two ways. Either the thumb points in the direction of the magnetic field and the curl of your fingers points in the direction of the current through the coil, or the curl of your fingers indicate the magnetic field on the inside of the coil, and the thumb points in the direction of the current through the coil. So if we look at the first one, A there, the magnet is stationary. Magnetic field line B1 is pointing away from the north. Remember, magnetic field always points from north to south. But the magnetic flux isn't changing, so no current is induced in that in that coil because the flux isn't changing. But then if we look at B, we see that the magnet is now brought downwards towards the coil. That means whenever a magnet moves towards a coil, the magnetic flux is increasing. Nature abhors a change in magnetic flux. So there's a secondary magnetic field that's going to be induced that counteracts that increase in magnetic flux. So if we look at B, we can see that the magnetic field is pointing downwards away from north. The magnet's brought towards the coil, so magnetic flux increases, so a second magnetic field is introduced or is induced that works against that magnetic field. So we can see that the orange magnetic field points in the opposite direction as the blue magnetic field. Just again, the blue magnetic field, that's the magnetic field of the magnet. The orange magnetic field, that's the magnetic field that's induced by the current moving through my coil. So we can use my right hand rule there. We see magnetic field of the magnets pointing downwards. Flux is increasing, so my induced magnetic field is in the opposite direction, so thumb points upwards, and then the curl of my finger is going counterclock or anti-clockwise through the coil, so current moves anti-clockwise through the coil. I can use my right hand rule in another way, with the fingers pointing into around the coil into the inside of my coil, counteracting the blue magnetic field, so the thumb points in the direction that my current is flowing through the circuit. Then with C, again I've got a north-facing magnet being taken that's close to my coil, but now it's moving away. When the magnet is taken away from the coil, my magnetic flux actually decreases. So now nature abhors that change in magnetic flux, so a secondary magnetic field is induced to counteract that change. And when magnetic flux decreases, that induced magnetic field will point in the same direction as the external magnetic field. Therefore, the blue arrow and the orange arrow point in the same direction. And then I can use again, now my fingers go into the coil downwards, so the electric current is going clockwise through the coil, as can be seen. Then in D, I've now just swapped the poles over. Now the south pole is at the bottom, north pole is at the top. The magnet is brought close to the coil. What that means is, again, magnetic flux increases. Nature abhors that increase. So again, like in B, the magnetic field is going to be pointing in the opposite direction. So we can see that B is now B2, that's the orange one. The induced magnetic field is pointing downwards. Therefore, the current is pointing again in the clockwise direction. And then lastly, as we can see there, the magnet is taken away from the coil, so magnetic flux is decreasing. Nature abhors that change. So the magnetic field is now both are pointing in the same direction. So the induced magnetic field is also pointing upwards. So the curl of my fingers up on the inside of my coil. Therefore, my current is flowing in the anti-clockwise direction. I want you all to go through these 5 diagrams. Make sure, especially B, C, D, and E, the last 4, and make sure that your right hand rule is telling you the same story as the diagrams. Just to reiterate or to recap here, if the magnet moves towards the coil, flux is increasing and the induced magnetic field will point in the opposite direction to the external magnetic field. Remember, the external magnetic field always points away from north and towards south. All right. Then we've got two rules. We've got Fleming's left-hand rules for motors and Fleming's right-hand rules for generators. We can call these also the FBI rules because the thumb indicates the direction of the force or thrust or motion. The pointing finger indicates the magnetic field or B, and then my middle finger indicates current or I, so therefore it's FBI. I use the left-hand rule for motors and the right-hand rule for generators. Let's have a look at an AC generator. For all of these, for motors or for generators, you must be able to give the energy conversion. And the energy conversion for a generator is always going to be mechanical energy that is converted into electrical energy. Remember, I'm spinning the generator, therefore I'm giving mechanical energy and I'm getting electrical energy back. Then an armature, you can see there's just a rectangular coil. Most generators are going to have multiple armatures, all right? And we can see there that the magnetic flux is given again by B times A times cos of theta. And then my EMF, I can simplify to number of coils, that's N, multiplied with electric field strength, B multiplied with the enclosed area of the coil, A multiplied with this weird little lowercase omega. That just means how quickly the coil is spinning. And then sine theta, that means that this whole equation is going to be a sine graph. So for an AC generator, it's literally going to be a sine graph. Starts at 0, goes up to its maximum at 90 degrees. At 180, it's back down to 0. At 270, it's at its minimum, and then back to 0 at 360 degrees. For a DC generator, instead of having the sine graph, it's going to look like a bunny hop. Everything is just positive. Then what are the components of my AC generator? We can see that I've got slip rings. Whenever I see slip rings and no battery, then I know that I've got an AC generator. The slip rings are attached to my carbon brushes, and what they do is they allow the coil to move freely whilst still conducting electricity to my external circuit. Now, let's use my right-hand rule. If we look at this diagram here at the bottom, we can see I've got a north side of a magnet and a south side of a magnet. So I say FBI. F is the direction that the side of the coil is moving. So the left-hand side of the coil will be moving upwards, because we can see it's moving clockwise. B, that's my pointing finger. That's going to be from north to south. And then my middle finger, is pointing into the board. So for this AC generator, in this current orientation, the current through the left-hand side of the coil is going to be moving into the board. On the right-hand side of the coil, now it's moving downwards. So thumb points downwards. Magnetic field is from north to south, so towards the right. And then current is pointing towards me, so the current is coming out of the board. We can see here my maximum EMF is given by the equation NBA omega. What this means is I can ask you, or we can ask you in the test or exam, how do you increase the amount of EMF of a generator? And there's 4 things you can do. You can increase the number of coils. You can use a stronger magnet, so to have a stronger magnetic field. You can use a larger area of the coil, so you use a bigger coil that's got a larger enclosed area. And then the last one, omega, that's the angular velocity. That's how quickly you spin the generator. So obviously the faster you spin the generator, the greater your EMF is going to be. All right, so your EMF is like your voltage. That's the amount of energy per unit charge that is produced by your generator. Then DC generator works in the same principle, except here you don't have a slip ring, you have a split ring commutator. And what that does is it reverses the direction of the current flowing through the coil, so that the output voltage stays in the same direction, or the output current stays in the same direction. And we can see it's like a sine graph here at the bottom, except it doesn't go underneath the x-axis, it stays on top. All right, so we've got like a bunny hop that it does. That's what the DC generator's EMF or current is going to look like, and that's because the split ring commutator disconnects each side of the coil, so that current flows in the same direction through the external circuit. All right, electric motors. Now we use our left-hand rule. First things first, what energy conversion takes place here? Of course, I am giving the motor electrical energy and I'm getting motion out of it. So the conversion there is electrical energy to mechanical energy. All right. And here we use our Fleming's left-hand rule. So if we look at this diagram over here, we can see again I've got a split ring commutator because this is a DC motor. If it was an AC motor, there would be slip rings. I've got a battery, therefore I know that it is a motor because I'm providing in electrical energy to it. I'm not getting electrical energy out. And if we look on the right-hand side of the coil, we see that the force is upwards. My magnetic field is from north to south, so towards the left, and therefore my current, my middle finger, is pointing into the board. And we can see that on the diagram there. Make sure that your left-hand rule and your right-hand rule for your generators, but here specifically your left-hand rule, that it matches the diagram. So on the left-hand side of the coil is moving upwards, or the conductor is moving up through the magnetic field. Magnetic field is pointing from north to south, so towards the left. and then the current is going into the board. All right. And then the same thing on the right hand side of the coil. My magnetic field is from north to south, current is coming out of the board, therefore the force is downwards. So it's rotating my motor, as we can see there, clockwise. Then we have to talk about our AC voltage and current. This is the second part of these types of questions. We can see that my voltage as well as my current form these sine functions. What that means is I've got a maximum or a peak voltage, a maximum or a peak current as well. But if I want to find out what the average is going to be, it's going to give me 0 because the top and the bottom is going to cancel each other out. So clearly using my average voltage to get some kind of an average or a mean is not going to work for us here. All right. So instead we look at our power. So power is current squared multiplied with my resistance. And when I square something like current, it's always going to be positive. Therefore, I don't have to worry about my average power going to be equal to 0. So my average power is just a half of my maximum power. And what this allows us to do is we can then calculate my VRMS and my IRMS. And RMS stands for root mean squared. And the way that I do these calculations is you take your maximum voltage and just divide it by the square root of 2. I find my root RMS current, I take my maximum current and divide it by the square root of 2. That's all I have to do to find my VRMS and my IRMS. Once I've done that, then I can use these equations with my power equations or my Ohm's law. So R equals V over I, for instance. We'll look at some examples of that in a moment. Then we've got some questions here. What are you expected to know regarding your AC current? Why alternating current is used for our mains electricity in South Africa? How is energy loss in transmission cables minimized? And how is the potential difference of the current varied? So let's have a look at those answers. We can see that current is generated in power plants and generators is delivered to users by means of connecting wires. Now, power is lost during this transmission, and the lost power we can see is equal to the current squared multiplied with resistance. So how can the loss of power be minimized? So what I do here is instead of having a high current, because if my current is high, then the power lost is going to be high as well. What I do is I increase my voltage. And with alternating current, I can increase and decrease my voltage using transformers. So that is why we use AC current everywhere in the world. We use AC current to minimize the loss of power through transmission. So what I do is after the electricity has been generated, I step up the voltage, I increase the voltage greatly so that the voltage is more, current is less, so that less energy is lost. Then once it gets closer to home at the substation, then I can step down the voltage again. I can decrease the voltage until I get to about 230 volts that comes out of the plugs in our homes. All right. So power plants and generators produce current with a high EMF. End users need current with a lower EMF. How do we reduce the EMF or the current? We're going to be using a transformer. Don't worry about this slide here. All you need to know is that the voltage is varied using a transformer. The equations for transformers are no longer in the curriculum. All right. We know that the frequency of AC current in South Africa is about 50 Hertz, and the potential difference varies from 0 volts to 311 volts thereabout. This has the same effect, but this means that we've got an RMS voltage of about 230 volts. All right. What we're going to do now is we're going to have a look at the November 2018 paper, question 10. You'll see that all of the question 10s, these are going to be the questions on your generators and motors, also your AC current or your AC alternating current types questions. So they say in 10.1, in the simplified AC generator below, the coil is rotated clockwise. How do we know this is an AC generator? It is not connected to a battery, therefore it is a generator. and we can see the slip rings, meaning it's an AC generator and not a DC generator. Remember, a DC generator would have had split rings. Here we've got slip rings, meaning they slide continuously, all right? Whereas your split rings are like two half moons where there's a separation between them. All right. Then in 10.1.1, in which direction does the induced current flow through the coil, from X to Y or from Y to X? So here we've got a generator, so I use my right-hand rule. Just to remind you, FBI, direction or force, magnetic field, and current. So I need to see which direction my current is going to flow. We can see the north pole of the magnet is on the right-hand side, south pole is on the left-hand side. Therefore, my magnetic field is going to be pointing towards the left. And on the right-hand side there, the coil is moving upwards, all right? So my thumb is pointing upwards. So the left-hand side of the coil is rotating upwards. Magnetic field is pointing from right to left. And therefore current, the middle finger, is pointing out of the board, out of the page. Therefore, my electric current is going from Y to X. All right, we can see there from Y to X, one mark there, very easy. All right, just going through that again. Magnetic force rather is going to be upwards. Magnetic field is from north to south, so from right to left in this case. And then the middle finger is pointing out of the board, so current is coming towards me, so from Y to X. Then they say in 10.1.2, on which principle or law is the working of the generator based? We can say there that it's going to be Faraday's law. All right, Faraday's law of electromagnetic induction, or we could say electromagnetic induction. We just say Faraday's law. That's what we have learned. And then in 10.1.3, state the energy conversion that takes place while the generator is in operation. We are spinning the generator, so we're putting in mechanical energy and we're getting out electrical energy. So for 2 marks there, very easy. It's mechanical energy to electrical energy. All right. I hope that that's clear to everyone. Then once we're done with our generators, you'll see then we've got another subsection. And here we give you the voltage output of an AC generator. So here's an AC voltage or AC type question. So they say we've got our voltage goes from 0 to positive 340, down to 0, down to negative 340, and back up to 0. And they say in 10.2.1, write down the maximum or peak output voltage of the generator. And we can read that off there immediately. It's 340 volts. I just read it off. It's just my maximum. It's the highest point of my graph. I hope we can all see that. Then they say a stove is connected to the generator above and delivers an average power of 1,600 watts. In 10.2.2, calculate the RMS voltage delivered to the stove. RMS voltage, how do I calculate that? I go back quickly and we see to find my VRMS, I take my Vmax divided by root 2 or square root of 2. So that's what I do here. I say VRMS is equal to Vmax divided by square root of 2. That gives me 340 divided by square root of 2, which then is 240.42 volts. Very easy, 3 marks there. Again, VRMS is just my Vmax divided by root 2. I put in my Vmax, I divide it by square root of 2, and I get 240.42 volts. All right. Then we go on to 10.2.3. They say calculate the resistance of the stove. I've got the power and I've got the RMS voltage. We've got an equation there. P average equals V squared RMS divided by R. It's just my power equation. All right. And I must use average power with RMS voltage. All right. So I just substitute that in. 1,600, that's given to me. The 240.42 is what I just calculated as my VRMS, and therefore my resistance is 36.13 ohms. I just solve that equation there. All right. We can see here, just quickly again, I give you a generator or a motor, you answer some questions regarding that. Usually there's an energy conversion stating Faraday's law or something like that. And then there's an AC voltage question or an alternating current question that comes afterwards for a total of usually about 10 to 15 marks or so. It's not a very big question. All right. That was the 2018 November paper. Let us have a look at the 2017 November paper. All right, so here they say the diagram below shows different positions A, B, C, D, and A of the coil in a DC generator for a complete revolution. The coil is rotated clockwise at a constant speed and a uniform magnetic field. The direction of the magnetic field is shown in the diagrams below. Write down the energy conversion that takes place during the operation of the DC generator. This is a DC generator because there's no batteries and there's a split ring commutator. We can see there's a split in those rings. It's not two slip rings that are next to each other. It's my split ring that forms the two half moons. All right. Energy conversion in a DC generator is, again, as we can see there, mechanical to electrical, mechanisch naar elektrisch. We can also say kinetic to electrical, but usually you'll see that we say mechanical to electrical. All right. Then they say sketch a graph to show how the induced EMF of the generator varies with time. Clearly indicate positions A, B, C, D, and A on the graph. All right, now this is going to form a sine graph, except it's a DC generator, so it's going to do the bunny hopping. It's not going to go above and below the x-axis. It's just going to stay above the x-axis. The only thing we need to figure out here is where do I start? And as a rule, if the coil is vertical, remember then the normal, all right, and the magnetic field is going to form a 0-degree angle between them. And sine of 0 we know is 0. So therefore at A, my EMF is going to be 0. Then at B, my normal is pointing upwards, magnetic field is pointing in the from left to right, so they are perpendicular to each other, so there's a 90-degree angle to each other. Sine of 90 is 1, so then it's going to be at a maximum. Then I've got the coil again in the vertical position, or the coil in a vertical position, so EMF is going to be 0. D, we're at a 90 perpendicular again. A, we're at I've got it in the vertical direction as well. So we can see here, ignore all the other graphs. We're just looking at this first one. That's the most correct one. We start at position A, 0, position B, maximum, position C, 0, position D, maximum, position A is 0 again. And that's just because of the alignment. We can see when the coil is vertical, my EMF is 0. When it's horizontal, it's going to be at its maximum or its absolute minimum, but we're obviously just assuming that I'm going from A, B, C, D, and A. So we can see that I've got starting at A at 0, B maximum, C 0, D maximum, and then A is 0 again. And then you can just see I've just said induced EMF and time in seconds. Make sure that your axes are labeled. You can see here the marks are just the correct DC shape starting from 0, and then positions A, B, C, D, and A correctly indicated on the graph. Let's go on to 10.2. A small AC generator providing an RMS voltage of 25 volts is connected across a device with a resistance of 20 ohms. The wires connecting the generator to the device have a total resistance of 0.5 ohms. Refer to the diagram below. Then 10.2.1, write down the total resistance of the circuit. So I've got a 10 ohm device or 20 ohm device or resistor, and then the wires have a resistance of 0.5 ohms. So of course the total is just going to be the sum of the 20 and the 0.5, so I get 20.5 ohms. All right. Then they say calculate the average power delivered to the device. Now what I need for that is power, of course. We can see here from my equations is equal to my current squared multiplied with my resistance. So I've got my resistance of the 20 ohm device. I'm not going to use the full 20,5 multiplied with the current. I'm just looking at the 20 ohm device. But first things first, I need my current. I've got my voltage and I've got my total resistance. And we can say then that current is my voltage, my RMS voltage divided by my resistance. That's 25 volts divided by 20,5. That's my total resistance of the circuit. And that gives me 1,22 amps. From there, ignore the equation on the left-hand side and the right-hand side. They're a bit unnecessary. We're just looking at this first one here. I've got the current through the device and I've got its resistance. I just say power average is equal to my RMS current squared multiplied with my resistance. That's just one of my power equations there. So I take my current that I just calculated, 1,22, and I square it, and then I multiply that with the resistance of the resistor, which is 20 ohms, and that gives me 29,77 watts. All right. I hope that that's clear to everyone. You can ignore the rest here. It's just a little, they're making it a bit more difficult for themselves. We just use the fastest and quickest method. Just to reiterate here, I've got my RMS voltage, I've got my total resistance. I calculate my RMS current then I use that current, I square it and multiply it with my resistance according to my power equation. If we have a look here at my data sheet, you can see here at the bottom, P average equals I RMS times R. So we're just using one of the equations that's given with the values that I have. Remember what we do with these questions. If we're unsure, we just make a little list for ourselves of all of the values that I know and the values that I want to calculate. All right. That's it for electromagnetism for now, or electrodynamics. What I'd like you to do, we've now done, as you can see, we've looked at the 2018 as well as the 2017 question 10. I'd like you on your own to have a look at the 2019 question 10. That's also going to be on generators and motors with AC voltage type questions. All right. If there are any questions, please don't hesitate to speak to me on WhatsApp or to message me. I hope that you all have a lovely day. I'm going to send some more videos in shortly. All right.